Good evening, everyone, and welcome to the Amateur Radio General Class, session number 14. During our previous class, we had a Q&A session. We did the question pool review. We started to look at some theories such as the standing wave ratio, matching network, and of course the related antenna tuner concept. We discussed transmission line loss and its relation to SWR. We also looked at transmission line loss and length and frequency, as well as parallel transmission line characteristics or characteristic impedances. We also had a look at the random wire antenna, also the half-wave dipole and its formula, as well as its radiation pattern. We also discussed the concept of feed point impedance, and then we went on to ground reflection loss, and finally we had a brief discussion on azimuth and elevation. So in terms of our curriculum, we are still under the topic antennas and feed lines. We will progress on that topic today. We will not quite complete. However, the next session, we should be able to finish and wrap up antennas and feed lines and continue on to the next topic. Again, urging everyone to continue taking the practice exams. We didn't have any unanswered questions from the last session. All of the questions were answered in class. So at this time, we will do a question pool review in relation to the theories that we discussed last session. So we go to our no-nonsense guide, and on the PDF version, I'm on page 38. So again, we will barrel through very quickly the questions. Okay, first up, what standing wave ratio will result when connecting a 50 ohm feed line to a non-reactive load having 50 ohm impedance? So dissecting this question, they're asking us what standing wave ratio, in other words, what SWR? So the answer will be some number to some number, or some number with a colon and a number after it. So it's the SWR they're asking us for. But they're asking us, we have a 50 ohm feed line and a 50 ohm load. So therefore, we had learned the last session, you put those two numbers side by side, divide them by one of the numbers, and you'll end up with a ratio. So it's 50 to 50, dividing it by 50, we end up with 1 to 1. Next question in the question pool. What must be done to prevent standing waves on an antenna feed line? Okay, so dissecting this question, what they're basically asking us is, we want to avoid a high SWR. We don't want standing wave on the antenna feed line, because that means that some of the power is reflecting back. We want all our power go to the antenna from the transmitter. We don't want any reflecting. And how do we do that? Well, the antenna feed point impedance must be matched to the characteristic impedance of the feed line. When that happens, you prevent the standing waves. Next question in the question pool. What standing wave ratio will result when connecting a 50 ohm feed line to a non-reactive load having 200 ohm impedance? Again, similar to the previous question, we have been given, they're asking us for SWR, so we know it's going to be a ratio. And we're looking for what are the two impedances that we're dealing with. We have 50 ohms and 200 ohms. So we put them side by side, divide both by 50, and we end up with 4 to 1. Again, worked example in the last session. Quickly, another similar example. What standing wave ratio will result when connecting a 50 ohm feed line to a non-reactive load having 10 ohm impedance? So again, the two impedances, 50 ohms, 10 ohms, we get 5 to 1. Divide both sides by 10. Okay. Moving right along. If the SWR on an antenna feed line is 5 to 1, and the matching network at the transmitter end of the feed line is adjusted to 1-to-1 SWR. What is the resulting SWR on the feed line? So I did mention that they were going to give us a trick question, and this is sort of a trick question because they're saying that the SWR on the feed line is 5-to-1. But then we adjust it to 1-to-1, and they ask us what is the resulting SWR. So you might be tempted to say, well, if we adjusted it to 1-to-1, then the answer is 1-to-1, right? No, remember we said that the antenna tuner, that matching network, makes it look as though the SWR has changed, but it actually has not changed. And that's the trick in the question. What is the resulting SWR? Well, it's the same as when you started. They told us it's 5-to-1. So the simple answer is 5-to-1. So don't get caught. Next question in the question pool. What is the interaction between high standing wave ratio and transmission line loss? So last class we said that if you have a high SWR, it will exacerbate your transmission loss. And that's the answer. If a transmission line is lossy, high SWR will exacerbate or increase that loss. Moving right along. What is the effect of transmission line loss on SWR measured at the input to the line? Again, we did this theory. The answer is the higher the transmission line loss, the more the SWR will read artificially low. So that means if you're using a transmission line that is very lossy and you have a high SWR, it might not appear high. It will be lower than it actually is because of the lossy transmission line that you're using. So that's why we're saying it will be appear artificially low. So again, all of these things that practical tips that hams need to be aware of, because that's what you encounter when you're using your radio, connecting it and transmitting and receiving and so on. Okay, how does the attenuation of coaxial cable change as the frequency of the signal it is carrying increases? Okay, let's dissect this question a little bit. So they ask us, how does the attenuation, remember attenuation is reduction, right, in signal. How does the attenuation of coax cable change as the frequency increases? So same coax cable, but we use one frequency, but then we increase the frequency to another one. How does the attenuation go? We learned that the higher the frequency, the higher the attenuation. So the answer is the attenuation increases. Higher the frequency, higher the attenuation. Next question in the question pool. In what units is RF feed line loss usually expressed? Let's dissect them. Short question, but let's dissect. What are the elements? They're asking us about the units. So we want to know in what unit? Unit of RF feed line loss. So RF is radio frequency, and we are looking at feed line loss. And we learned that the longer the cable, the more loss you have. So the loss is given in dBs or decibels per 100 feet. Okay, moving right along. What is the typical characteristic impedance of window line parallel transmission line? Okay, and we learned that sometimes window line is called ladder line. We learned last session that that ladder line is 450 ohms, what is called window line. We learned about a couple others and what the impedances were, but note that window line is 450 ohms, characteristic impedance. Moving right along, next question in the question pool. What is one disadvantage of a directly fed random wire antenna? Okay, let's dissect it a little bit. They're asking us about a disadvantage. Not an advantage, a disadvantage. Of what type of antenna? Directly fed, random wire HF antenna. And we had a diagram last session showing what that actually looks like. And we said with that, if it's directly fed, the wire comes straight into the house, to the antenna tuner. You may experience radio frequency burns when touching metal objects in your station. And that's because you'll have the presence of RF in your station. That's a disadvantage of having the random length of wire as your high frequency or your HF antenna. Safety first. Next question. What is the approximate length for a half-wave dipole antenna cut for 3.550 megahertz? that relation to the half-wave dipole formula that we learned last class. So we simply plug that in. L is equal to 468 over F, and L is the length, and F is frequency. We plug that into our trusty formula, magic formula, and we get 182 feet. So worked example in the last class. Next example, again another worked one. What is the approximate length for half-wave dipole antenna? Cut for 14.250 megahertz. Use our magic formula again, plug it in, and we end up with 33 feet. Again, another worked example in our last session. Moving right along, how does the feed point impedance of a half-wave dipole change as the feed point is moved from the center towards the ends? Let's dissect this question a little bit. So we had a diagram showing a half-wave dipole where the feed point was exactly in the middle, and we had the two legs, and we said that if we were to change that feed point, in other words, it's no longer exactly dead in the center, it's to one side, it's off center, we start to go towards the end instead of in the middle. We say when we do that, the feed point impedance, the feed point impedance increases as you move towards the end. So let's move right along. Next question. Which of the following is an advantage of a horizontally polarized as opposed to a vertically polarized antenna? Let's dissect this question. So they're asking us about an advantage. But advantage of what over what? Horizontally polarized as opposed to vertically polarized antenna. We said that one advantage of it being horizontally polarized is that you get lower ground reflection losses. That's an advantage of horizontal versus vertical polarized antennas. All right. Next question in the question pool. What is the radiation pattern of a dipole antenna in free space in a plane containing the conductor? All right. So that's a little bit of a, make it sound very complicated, but we had said that the radiation pattern, it's figure 8 and it's at right angles to the antenna. So we had showed a diagram that showed what the radiation pattern was. We had a nice little cardio diagram and you saw the 8 in it, so that's called a figure 8, and it was at right angles to the antenna. So again, have a review of last session's video or slides to have a look at that. Okay, next question. How does antenna height affect the horizontal or azimuthal radiation pattern of a horizontal dipole HF antenna? Okay, so that sounds like a complex, complicated question, but let's break it down. It's quite simple. You know this. What are they asking us? They're asking us how does the antenna height affect the horizontal or azimuthal radiation pattern. So remember we took a little time out to talk about the difference between azimuth and elevation and so on. So this is why we did that. So when they give you these terms, horizontal, azimuthal, you know what it means. It means just, looking left, right, instead of up or down. That radiation pattern, horizontal, for horizontal HF dipole. And we learned that if the antenna is less than half wavelength high, meaning that the height of the antenna above the ground is less than a distance equal to half of the wavelength of the frequency, then the azimuthal pattern, that is the horizontal pattern, is almost omnidirectional, meaning that the antenna will radiate about equally in all directions. That's what omnidirectional means, and you need to know that for your exam, and that's the answer to the question. Let's do a last question before we go into some theory. How does the feed point impedance of a half-wave dipole antenna change as the antenna is lowered by below quarter wave above ground? So let's dissect this question. They're asking us, how does the feed point impedance change? So they want to know, does it increase or does it decrease? But what of a half-wave dipole antenna as it is lowered below quarter wave above the ground? In other words, you're limboing below quarter wave. The distance of that antenna above ground will be lower than quarter wave length. And we learned last class that when we do that, the feed point impedance, what does it do? Does it increase? No, it decreases steadily as we limbo down, as we go lower. According to Kess, as you go lower, it decreases that impedance. All right. So let's go now to our slide deck and pick up some theory. All right. Okay, so back to our trusty slide deck. We had no questions from the last class. All right, okay, good. Next. Slide deck continuing. Antenna types, quarter wave. So one of the types of antennas, we have been dealing with different types of antennas throughout the course, and we are going to talk now about the quarter wave antenna. In the technician class, we would have encountered some of these types of antennas before. So it's really building on your knowledge. So feel free to refer to the technician class material for foundation information. So we are talking now about the quarter wave antenna. Last class, we talked about the half wave dipole. So these antennas are given in respect of the length of the antenna relative to the wavelength of the frequency that is being used. So quarter wave antenna. The quarter wave ground plane vertical antenna. It consists of a radiating element that is quarter wavelength long, and that's how it gets its name, as a quarter wave antenna, and it's also vertical. But guess what? This is how it's constructed. If we were to look at the screen, you will see this vertical antenna, this element that they are referring to is the radiating element. It's quarter wavelength long. But notice there are other elements to the antenna, and these are called the radials. They are also quarter wavelength long. And of course, we have our feed line going to the feed point of the antenna. That's what this quarter wavelength antenna is. So you have the driven element, or you have the vertical radiating element, and you have your radials. The length, how do you know if you want to construct one? You just find what operating frequency is, and you work out quarter of that wavelength, and that is going to be the length of the antenna. Now we need to know about some properties of the quarter wavelength antenna, and we have some other diagrams to illustrate those properties. First of all, a quarter wavelength antenna like this radiates the transmission or the signal in all directions, omnidirectional. Remember we said azimuthal, you just look left or right. So in all directions that you look at, the antenna will be radiating. So if we were to look at the pattern here to the right, you'll notice that this is the antenna at the center, and this is the signal all around. So it's equally radiating all around in all directions outbound. At north, east, west, south, northeast, everywhere, it's equally radiating in a horizontal direction or in an azimuthal direction. The other property about the quarter wavelength antenna is that there's a low angle of radiation. So that's actually an advantage. And when you have a low angle of radiation, your signal reaches further. And let's look at the diagram on the right-hand side here. Notice this is our Earth, and this is our ionosphere. Some of you who are in the technician class or reviewed the technician material will know about the ionosphere. And we know hams bounce. We love to bounce things. So we bounce off the ionosphere. We reflect the signal, really and truly. We refract the signal of the ionosphere. So if this is my position on Earth and I am sending a signal that is at a high angle of radiation, it will go up to the ionosphere and it might bounce down short here. But if I have a low angle of radiation, takeoff angle is low, it goes this way instead of straight up. It goes this way, a low angle of radiation, and bounces off the ionosphere, and look how much further the signal goes. So that's what we mean by a low angle of radiation. A high angle of radiation is up, up and away towards the sky, straight up or almost that. A low angle is more towards the horizon, sort of straight ahead. It's still to the sky, but it's a low angle of radiation. So you know, sometimes you look up at the moon or the sun and you say it's above, or star, it's above, right? That's a high angle. But if it's at the horizon, you're looking at it towards the sea or towards the land, and you're seeing it straight ahead, that is a low angle. So what we're saying is that the quarter wavelength antenna, one of the advantages is that the angle of radiation of the signal is relatively low. And when it's low, just like this diagram we showed here, your signal can reach further. So like everything else, we have to have a formula for something, right? So we had previously in our class dealt with the formula to calculate the half-wave dipole length. So we now come to the formula for the quarter wave antenna. And this is our trusty second magic formula. L is equal to 234 divided by F, or some will say 234 upon F. And that is our formula for quarter wave. But you might be saying, but wait a minute, that formula looks awfully familiar. Did we not do something like that last class? Yes, we did. We did L is equal to 468 over F, but that was for the half wave. And then if you did a quick calculation of, wait a minute, 234 is not half of the 468, you would be quite correct. And that's it, because quarter is half of half, you have half of the number on top. So you have L is equal to 234 upon F. The other formula for the half wave was L is equal to 468 over F. So there we go. Easy peasy. That's the quarter wave formula. And we will do a worked example very shortly. How do you calculate? And what are we calculating? The length of the element. This is our antenna. The vertical driven element, if you want to call it that. Vertical radiating element. And then you have the radials that go out from the feed point. And we are calculating how long is this element is going to be. How long is this radial going to be. All of these radials. And we say they're all going to be quarter wavelength. So we therefore need to work out what that length is. And we can do so using the trusty formula. Well, length is equal to 234 over F. And F is the frequency that you're trying to build the antenna for. You want it to be resonant. You want it to match the frequency. So F is that frequency. Let's go to the worked example. And this is an actual question in the exam. What is the approximate length for a quarter wave vertical antenna cut for 28.5 megahertz? So before we do the actual calculation, notice that we're using the lingo. The antenna is being cut for. So that means you're building the antenna. You're cutting it for this frequency. You want the antenna to be resonant in this frequency. Why? Remember, say we're Hamza matchmakers. We want to make sure that we have maximum transfer of our signal. When that antenna is resonant to the frequency that we are trying to transmit, beautiful things happen. We waste very little or no wastage is involved, and most, if not all of our signal goes out and leaves our antenna and goes into space, goes and across land and reaches the other amateur radio operator that we want to communicate with. Maybe it's a conversation that we're having, a friendly one, or maybe it's an emergency operation and we're trying to get an emergency communications message across. But we want to do so with efficiency and effectiveness, and that's why we calculate things like the length of what that antenna should be if we're going to use the frequency of 28.5 megahertz. So let's calculate it. L is equal to 234 over F. That's our formula. Trusty magic formula number 2. So all we do, we say, okay, L is equal to 234, which is a constant over the frequency. Did they give us the frequency in the question? Yes, they did. 28.5. We plug 28.5 where F is, and we end up with L is equal to 234 over 28.5. Convince yourself, use your trusty calculator, and you'll see that the answer is approximately 8 feet. So therefore, an antenna that is a quarter wave design that is cut for the 28.5 megahertz frequency will be 8 feet long. From the feed point to the top will be 8 feet. The radials, those horizontal radials as they are shown here, will be 8 feet also. So speaking of quarter wave antennas, we can mount quarter wavelength antennas on the ground, especially HF antennas. It's done. So we say that when we have a vertical antenna such as a quarter wavelength and it's mounted on the ground, notice the radials here. The radials should be placed either, and this is an exam question, so you need to know this, either on the surface of the earth, as you're seeing here. So these are the radials. This is our vertical element of the antenna. Some people think this is the antenna. All of this here is just the antenna, but the antenna also consists of the radials, right? The radials need to be either on the surface of the earth. See how nice and evenly they are spread here? Or it can be buried, but only a few inches below the ground. Don't send it 6 feet below. Just a couple inches will be fine, because there's a consequence if you were to send those radials too low below the surface of the earth. And that is this bullet point here. If the radials are they should be buried. If the radials are buried too deeply, the radials may cause ground losses. So you don't want to bury it too closely. When I send out the slides, I will correct the spelling. It should be buried. You want it just on the surface if you can, like you're seeing here, or just below the surface, maybe a couple of inches, but no more than that. And you need to know this for the exam. Continuing on the quarter wave antenna. So as we have learned before, at the point where the feed line or coaxial cable, whatever your transmission line is, connects to the antenna, that's called the feed point. And we have learned that at that point, we need to know what that impedance is, because our feed line or coaxial cable is typically going to be 50 ohms. And we said hams are matchmakers. So we want that feed point at the antenna to be what? 50 ohms also. But here's the thing. A typical quarter wavelength antenna, the feed point impedance is only 35 ohms. Oh, so that is not good. We said hams are matchmakers. So we want that feed point to be as close as possible to 50 ohms. So we'll have a good SWR. We'll have maximum transfer of power. We don't want to have any reflection, any damage to our equipment. Hams are matchmakers. So 50 ohm feed line, but 35 ohm feed point for quarter wave. That's not good. This is the antenna useless. Here's what we can do. We can actually adjust and increase the feed point impedance to the desired 50 ohms. That's what we're aiming for, because hams are matchmakers. By simply sloping these radials. So on our right hand side here, notice the same quarter wavelength antenna, quarter wavelength elements, but notice they are sloped downwards. When you slope it, you increase the feed point impedance. So that's a technique that hams use. We slope the radials, and guess what? We can get it to where it becomes 50 ohms or very close to 50 ohms, and we get a nice SWR, maximum transfer of signal, and we have a very good feed point. There we go. So we have been talking about omnidirectional antennas, antennas that transmit in all directions. We're coming now to antennas that are specifically or intentionally directional. We want to send our signals in one particular direction or towards some place. You know, you're not just throwing an arrow somewhere and hoping it lands somewhere. You're saying, you know what, I want to head in this direction. So we use a directional antenna. Now, the directivity of a signal results in gain in the given direction for both transmit, and you also are more sensitive on the receive side. So that's what happens when you use a directional antenna. Your signal, notice where we have here an omnidirectional antenna as before, the signal goes in all directions. It goes east, west, north, and south, and so on. But notice for the directional antenna, I want my signal to go in one direction. So my signal will be concentrated, most of it going in this direction. So therefore, the signal should read further, and we call that gain. Also, I will be more sensitive when I'm receiving in that direction also. So I will get weaker signals a little better and so on. And I will also be rejecting signals towards the back of me, because I'm not that sensitive to it towards the back, but towards the front here, or the direction, my intended direction. I'm very sensitive on the receive, and I'm also very strong on the transmit. I have gain. And we said that that property of directivity can help us in minimizing or overcoming sources of interference. So if I have interference behind me, I use a directional antenna and I point it away from the source of interference. And that is a question in the exam. They will ask you, how can you minimize the source of interference? And the answer is to use a directional antenna and you turn it away from the interference. So that's how all of these these techniques help us to avoid interference. And we note here that examples of directional antennas are Yagis and quads. We covered a bit about it in the technician class, so this should be a bit familiar to you. We have the Yagi and we have the quad, and we have a couple of slides that will deal with those two types of antennas when we come back from our break. So folks, let us take a short 2-minute break. Get up, take a stretch, maybe have some water, do a bathroom break if necessary, and meet you back in 2 minutes. Okay, everyone, welcome back. And we have a couple of questions that we will deal with before we move on to the rest of the theory. So Adish asks, would the length of that antenna be for the frequency that is needed or the entire band with those range of frequencies? Excellent question, Adish. So we have two concepts, some of which we haven't really talked about or discussed yet, and we will comment a little bit in a slide later on. But there are two concepts here. One, really an antenna is going to be resonant on a particular frequency. Left or right or above or below that frequency, it's going to be less resonant. But there's also the concept of the bandwidth of an antenna, where an antenna could be pretty much resonant over a wider range of frequencies. But generally, for some of the frequencies that amateurs are using, the bandwidth is so wide that you will hardly find that there's an antenna that is going to be exactly resonant across the whole range. That is not typically what you will get. But yes, you can have some antennas that are reasonably resonant over a range of frequencies or part of a band, but it hardly ever is going to be perfectly resonant on the entire band. It's not going to be, and that's why in the case of HF, you'll use antenna tuners and so on. Sometimes you can tolerate a high SWR or a higher SWR and so on, but generally you're really aiming for resonance as well. So not really. The antenna that's cut is cut for a specific frequency, the one that you're either going to be using regularly or sort of snap dab in the middle of the band so that it's likely to be as resonant or as closely resonant as possible. But if there's a particular frequency that you use, I would say cut the antenna for that particular frequency. If it's going to be more general purpose, you can then design and say, well, here's what, let me cut it for snap dab in the middle of the band. If it's 2 meters, for example, centimeter. If it's HF, that's usually where an antenna tuner will come in. Many hams will tune and snip that antenna to be really resonant without an antenna tuner on that frequency. And it'll be not so slightly higher SWR left or right or up and down of that frequency. And if they really want it to be, if it's too high, they will employ an antenna tuner. And there are some properties of antennas that will come in a little bit where depending on the element that you use, it tends to have a slightly higher bandwidth than if you use, let's say, thinner material for the antenna. Cool. Fantastic, Adish. Glad. And Jermaine asks, what is the effect of having many ground plane elements or radials when the quarter wave antenna is placed on the ground as opposed to force slope radials when the antenna is mounted above ground? Excellent question there, Jermaine. So what I may have neglected to mention is that when it's up in the sky and you're sloping the elements, that is usually for VHF, UHF bands. One will hardly ever put a VHF, UHF antenna on the ground per se. So normally on the ground antennas we're talking about is really HF antennas where the lengths are much, much longer. The shorter antennas and also how the radio frequency propagates for VHF and UHF, you really want height. Height is might when it comes to those frequencies. But for HF, I mean, you could have an antenna on the ground and it will radiate. So really in terms of the HF, it's not really either or. Not that you can't do it, but optimally VHF and UHF antennas are put way above the ground. That's the idea, above all objects and so on. But HF antennas, there can be designs where you have them right on the ground, ground mounted, exactly as you saw in the picture. So the force slope radials are for usually those VHF, UHF type antennas. And the HF antennas tend to be where it's ground mounted and you have those radials. They do put them, copper radials, copper wire on the ground or in the ground to get a better transmission, lower noise floor and that sort of thing like that. So you tend to have hams who can afford it will put several radials. So it's not as though you slope radials for HF, and typically the antennas with the sloping radials really typically don't go on the ground in any event. So excellent question, but I didn't differentiate between the two instances. But really, really good question, Jermaine. I hope that has helped a bit. And if not, just message me or send me an email. Okay. All right. Fair enough. Thanks a lot, Jermaine. Glad it worked out there. Cool. So, folks, let's go continue with the theories. And just to say, okay, this is what our Yagi antenna looks like. And this is an example of what the quad looks like. And we'll deal with those two antennas a little more shortly. So we need to be familiar with the concept of gain. We have been talking about gain, not the liquid that you use, not that gain. The gain antenna we have been talking about it as a very good thing for quite a while in our classes, in our sessions. We've been saying antenna gain. It's a good thing. But how is gain actually measured? Gain is measured in decibels or dB. We came across the dB or the decibel measurements previously. But specifically for antennas, we will measure the gain in either dBi or dBd. dBi is simply the decibel of the gain of the antenna relative to a theoretical ideal antenna called the isotropic antenna. It doesn't exist really, right? It's a theoretical concept that you think of as an ideal antenna, where that antenna is going to radiate the signal like a spherical radiation, exactly the same in all directions, up, down, left, right, center, and so on, you know. Like a spherical type radiation, not horizontally, not all around equally. And that hardly ever is going to exist in any real world, but it's a good theoretical concept. So antenna gain can be given in dBi. And as we'll come to in a little while, some antenna manufacturers give it to you in dBi. Why? Because that number is higher or bigger. And for marketing, they may want it to sound bigger, right? dBd is the gain of the antenna relative to a dipole antenna. So the reference is the dipole. And therefore, if your antenna has gain above it, it's how much relative to the dipole. It's kind of like I'm saying I'm taller than Ishmael, right? So I'm taller than Ishmael. So whatever height Ishmael is, I'm taller than him. Or I might say I'm taller than Desi. I might be taller than both of them, but I may be using Ishmael as the reference. I'm taller. I might be much taller than Ishmael, but I might just be slightly taller than Desi, but I'm taller than both of them. So I can tell you I'm taller than Ishmael, and I'll say, okay, I'm 3 feet taller than Ishmael. Sounds impressive. Then I might say, well, I'm only 6 inches taller than Desi. Not as impressive. But I'm the same height. My height hasn't changed. It's just who is my reference. I'm taller than what? I'm taller than whom? And the same thing with the antenna. The gain is relative to the isotropic or the dipole. And we also share with you here that the gain of a dipole will be 2.15 plus whatever the gain of the dipole is. So dBi, or did I say that correctly? The isotropic rating or the gain with respect to the isotropic is going to be 2.15 more than the gain if you reference a dipole. So that's why some manufacturers, marketing will tell you, well, you know, you have a 9 dB gain. 9 dB what? Is it dBd or dBi? And when they say, well, it's dBd. Sorry, it's dBi. Oh, so that 9 dBi is actually more like 7 dBd then. So it's really a 7 dB antenna, not a 9. But you tell them a 9, but you just didn't tell me whether it's I or D. So, you know, we always need to know relative to what. Something is more than something, but relative to what. So just note that gain is measured in decibels. And gain, and we have a little diagram here to show a little idea of gain compared to omnidirectional. Notice if you have a light bulb, it kind of goes and illuminates in all directions. But if you have a flashlight, you concentrate in that light in one direction. And that's the concept of directional antenna. It might be the same bulb, but you're taking all of the energy and trying to send it to one direction. That's what we do as hams as well with our radio signals. Let's concentrate it and let it go in one way. And we have a little reference point here. Sometimes it could be confusing. What is isotropic? What is dipole? So we show here, this is the isotropic radiator, ideal. This is how it operates. It's theoretical and it's perfectly radiating in all directions. And you have more practical down to earth. This is a dipole. It radiates in all directions horizontally. But notice it's not as perfect as an isotropic. It's just 360 all around horizontally or azimuthally, as you had learned earlier. And that's the dipole. So when we are given gain, so here we have a directional antenna, maybe the Yagi. It's sending most of the signal in one direction. But relative to what? The dipole or the isotropic, we give the gain and we need to know which one of the two. So for your exam, you need to know about dBi, dBd, and you need to know how to calculate dBi given dBd. And this is our formula. dBi is equal to dBd plus 2.15. So let's continue about gain again. This time we deal with the concept of front to back ratio. All right, Tezzy. Yeah. So let's go. Front to back ratio of a directional antenna, such as a quad or a Yagi, is a measure of directivity it's also a measure of the gain. So the greater the front to back ratio, the more directional it is. The greater the front to back ratio, the greater the gain. So when you hear front to back ratio, we are talking about a directional antenna. How directive it is, how much gain does it have? How much of that signal is it throwing into one direction versus another? Okay, so the ratio compares the power radiated in the forward direction of the main radiation lobe, and we have a diagram showing that there, to the power radiated at the back or the opposite direction of the antenna. So if this were to be our antenna here, and we are sending most of the signal, this is our frontal lobe or front lobe, or where our directivity, we want that direction, we want to receive, and we also want to transmit in a direction. So notice the signal is going mostly here. We do have some side lobes. No, things aren't necessarily perfect, so we put that in to show you that there are also some side lobes. It's not as though they're just two lobes, front and back. So you have the front lobe, but notice how big it is. And we have the back lobe. So notice that very little signal compared to what is going to the front here. So most of it, just like the flashlight, you want your signal to go here. And therefore, that front to back ratio, the power that is going towards the front versus the power that's going towards the back, we refer to those things as the front to back ratio, directivity and the gain. And we need to know that the main lobe is the direction of maximum radiated field strength from the antenna. So read that as maximum amount of signal. So this is our main lobe or our front lobe. Again, it's an exam question. So let's go to the Yagis. What is a Yagi? Yagi-Uda, all right, gentlemen, it's named after. The Yagi antenna is very, very, did I say very? Common in amateur radio operations because you have gain. Of course, you don't get something for nothing, but you are able to concentrate your strength into one direction. Right? Those of you who do martial arts, you will know that what you're trying to do is maximize your impact in a particular direction. You don't want to waste that power. So we do that in amateur radio as well. So we use directional antennas on the Yagi, relatively easy to build, and we use it to concentrate our signal in one direction. This is what a Yagi looks like. This is an actual antenna. This is a diagram showing how it's constructed. And we need to know about the structure of a Yagi. There are some terms that refer to the parts of the antenna. So the Yagi comprises of the boom. The boom is this element here that you're seeing on the screen. It's the where the other elements are connected to. So basically, it's like the foundation of the antenna, really, where all of the other elements either attached to, connected to, screwed onto, clamped onto, and so on. So that is our boom. We have the driven element, and that is our main radiating element. And if you were to say, but wait a minute, this looks like a dipole, you'll be correct because it is. So that's your driven element. So you realize the Yagi is really like a dipole with extra elements, huh? Yeah. And those extra elements are called parasitic elements. Yes. And within those parasitic elements, depending on where it's located relative to the driven element, so you have a little dipole here, part of the Yagi, and you have elements behind it and in front of it. And if it's behind it, it's called a reflector. And if it's in front of it, it's called a director. And we need to know for the exam that relative to the length of the driven element, your reflector will be longer by 5% actually, 5% longer than the length of your driven. And your directors will be shorter. So you think of it like a pencil point. You know, that's exactly how it looks. So the direction that you want to face is going to be shorter and to the point. So think of it as a pencil point. You're pointing in a direction. So you need to be sharper in the direction you're going to. It's like an arrow. So it's wider at the back and narrower at the front, the direction that you're facing. So you have your driven element. You have a parasitic element such as the reflector at the back. And then you have directors. You could have several of them towards the front and they get shorter. The first director will be 5% shorter than the driven element. And so on. They get shorter as you go. But the reflector is 5% longer. The driven element is the length of it, the wavelength, and then 5% shorter for the first director. The length of the driven element is calculated using our trusty half wavelength formula. So half wavelength of the frequency of operation is what you're aiming for. And you'll be correct. Same as the dipole. There you go. It's a dipole with wings. All right. Now we need to know a bit more about our Yagi antenna. Of course, as hams, we wouldn't just go off the shelf and buy an antenna. We build antennas. So we need to know a bit about how do we design it, how do we build it physically. And we need to know for the Yagi antenna, this is a diagram of it towards the right here. Again, another representation. You have your driven element, see that here? This is the driven. You have your reflector, and then you have other towards the front here, and these are our directors. So notice reflectors and directors are considered parasitic elements. The driven element is the main element. You have our boom. So again, another diagram to show you how it's constructed. But we need to know, and this is related to Adish's question, that for the driven element, if we increase the diameter of the element, and it's typically made out of aluminum tubing, that's the material, it's easily available, it's relatively inexpensive, and it's easy to work and cut. If we increase the diameter of this element, it's the thicker it is, the fatter it is, we increase the bandwidth of the antenna. Adish was asking, okay, when you cut it, is it resonant across the entire band? Well, the more resonant across the band you want it to be, you use a thicker element. Of course, there are practicalities involved. I mean, how thick and fat can you go? But if you want it to be more resonant across a wider range of frequencies other than the resonant frequency, you increase the diameter of the element. And that causes the bandwidth of the antenna to be increased. That's an exam question, and it's exactly what Adish was asking earlier. Also, if we increase the boom length, this length here, and we add additional parasitic elements, so directors, more directors, we increase the gain of the antenna. So you want more gain? Add more directors. So you might have a 3-element beam, 4-element beam, 5-element beam, 27-element beam. Yes, hams do that sorts of thing. And you will get more gain. So you increase the boom length, add more directors, and you got more gain. Exam question. Now you can also adjust the physical length of the boom, the number of elements, and the spacing of the elements. And when you do that, you're optimizing, you're getting more gain, you're getting better front to back ratio, and you could be adjusting the SWR and bandwidth also of the antenna. So that's what hams do: design, optimize, change lengths, change distances, add more, subtract, and optimize, all to be able to communicate, get our signals farther, and be able to have better signals. So you don't always have to drive more power from a transmitter. You don't have to send, okay, I'm running 100 watts. Let me run my legal limit, 1.5 kilowatts. The authority, FCC or TAT, whoever gave you that permission. But in hams, we say run only as much power as necessary. So you don't have to drive power alone to get your effective radiated power up. You can use these antennas with gain and throw your signal a little further using less electrical energy, but you're optimizing with your antenna. And that's what you're doing when you use directional antennas. Oh, guess what? There's another thing else you can do with Yagi antennas. You can stack them, just like boxes or pallets of cases of water. You can stack one on top of the next. Yes, you can stack Yagis. Stacked Yagi array here we've got. So one improvement that we can do is stack one Yagi on top of another, and that's what it is here. And we need to have a distance between the two Yagis, and we say that when you stack them half wavelength above each other. And when you do that, you have a very nice optimization. So if you stack two of these 3-element Yagis, so 3 elements, element 1, element 2, element 3, you have the driven element, as we call it, we have the reflector, and we have the director. That's a 3-element Yagi or 3-element beam. So we take 2 of those 3-element beams or 3-element Yagis, and we stack them one on top each other horizontally, polarized antennas, and we stack them vertically, and we separate them by half wavelength. That is what this bullet point is talking about here. And that causes this signal to travel even further when we stack these 2 antennas. Look at that. Are we getting something for nothing? Maybe, maybe not. But we are, as hams, looking to eke out every single watt of power and maximize its use. We don't want to waste it, and we want to direct it. And this is one way that hams do it. We stack the Yagis. And when you do that, the gain is increased by 3 dB. Just stacking these 2 compared to one antenna, you have a gain of an additional 3 dB. That is very significant. Also, the main lobe elevation is narrowed. Remember we said when you have that narrowing, your signal is going to reach further, and that's why we put back up this symbol here, this diagram, to show you that when you narrow that lobe and you send it lower angle of radiation as well in narrowing the lobe, it's going to go further, and the signal is going to travel a further distance, which is your intention. So you need to know these points in yellow for the exam. Again, we talked about it, that your antenna needs to be matched. We say hams are matchmakers, but how do we match the feed point? Remember we said that the feed points are not necessarily, we talked about it with the quarter wave, it's not necessarily 50. We're trying to aim for 50 because our feed line is 50 ohms and we want to match. Why? Because hams, we are matchmakers. And the feed point of a Yagi is actually much lower than the ideal 50 ohms. It's not 50 ohms. Why is it lower than 50 ohms? Because it's because of the parasitic elements. You see those elements you add in there, the directors and the reflector, that is causing that feed point impedance to drop way below 50. But you want it to be 50. Well, magic question. How will a ham match? Well, we are matchmakers, so we match the feed point to make it 50 ohms. We use several things we can use. One of them is called a gamma match. And on the right hand side, you have a picture of what it looks like. You have the element here, and then you have this piece of construct here that allows us to tune this stub and match the impedance. This is a diagram as to how it looks for 2 meter gamma match. And this is just for your information. You don't necessarily need to learn this for the exam, but you like to give a little extra in the course so that you see what it is, make it real. And this is what the diagram, if you have to construct one, look, the dimensions are here for you. And this is what it actually looks like on a real antenna. But you just need to know that a gamma match is used to adjust the feed point from the less than 50 ohm it is by design. And you add this gamma match and you can tune it such that it becomes 50 ohm at the feed point. Why? Hams are matchmakers. You're trying to match that 50 ohm of the feed line and of course the transmitter. Now, an advantage of using a gamma match for a Yagi is that it does not require the driven element, that's the main element here, to be insulated from the boom. You don't have to insulate it at all from the boom, and you need to know that for the exam because it's an exam question. All right, we talked about the gamma match, but there's also a match called the beta match, also known as a hairpin match. And this is how it looks on an antenna, a real antenna. It's a piece of transmission line. You say, but wait a minute, that looks like a piece of coax. You'll be quite correct. It is a piece of coax, except that it's shorted here. It's a length of feed line. And guess what? That is your match, a beta match, also known as a hairpin match. And this is a little diagram as to what it looks like. You have your feed line coming in here, and you have your little hairpin match here, and it shorts the 2 elements left and right, and this is your feed line. This is how it's made up, the hairpin match. But what you need to know for the exam is that it's consisting of a shorted transmission line stub. So this is the transmission line. Remember we said transmission line coax cable, and it's shorted. Notice the short here, it shorts the 2 elements. And it's placed at the feed point, because notice this is the feed point here. This is the so 239 connector what you're going to bring your feed line to on your antenna. So that's the feed point. And the stub is at the feed point of the Yagi antenna, and it provides impedance matching. Again, hams are matchmakers all day, all night. Another type of antenna that is also directional is called the quad. So similar to the Yagi, it's directional. A quad antenna consists of square loop elements instead of just simply vertical or horizontal elements. It's square loop. So this is what it looks like. So those of us who were in the technician class would remember that this is what a quad antenna looks like. Square loop. We need to know for the exam that the length of each side of the driven element, that's where the feed line goes to, the length of each side is exactly a quarter wavelength of the frequency of operation. So this diagram shows us here that the length of a side is quarter wavelength. It says it, each side quarter wavelength. And we have our feed line that comes to feed our driven element and it's quarter wavelength each side. Now there's an advantage of the quad is that for its size compared to the Yagi in terms of number of elements, you have the same amount of gain for if you have, let's say, a 2-element Yagi, sorry, a 3-element Yagi, a 2-element quad will have about the same gain. So what we say is that that's an advantage given the quad will have a greater gain compared to a Yagi. the quad will be physically smaller. A 2-element quad has about the same gain as a 3-element Yagi. All right. So you need to know this for the exam as well. For a 2-element quad to operate as a beam, meaning that you want it to be directional. Now, this is a 2-element quad we're talking about. So it only has the radiating element or the driven element and one other parasitic. That will be the reflector, and you need to make sure that it is 5% longer. It's very similar to the Yagi calculation. Remember, so the reflector in a Yagi needs to be 5% longer as well. So it's the same 5%. So the reflector in a quad also needs to be 5% longer for it to be directional, or as they say, to operate as a beam. So that, folks, is our last slide of the slide deck. We'll deal with any of the questions that persons have posted in the subsequent session. So, folks, thank you very much. Again, persons, we encourage you to review the technician class videos. That's the link. I'd like to congratulate a couple of the persons who took the technician class. We have gotten some really good results. Persons have sat the FCC exams, passed it, and they've also applied in Trinidad and Tobago for their local call sign through TAT. And we have a couple of newly licensed 9 Zulu 3 call signs. So congratulations, very well done. Really impressed with you. Sticking to it, seeing it through, and getting your license, and you're now considered amateur radio operators, ham radio operators, and you can now get on the air. You have a license to experiment, you have the theory behind you, and you can now go forward. So, folks, thank you so much. Our next session, God's willing, will be Friday the 16th of July 2021. Usual start time, 8:30 p.m. Take good care, everyone. Be safe. All the best, and keep in touch. Okay, Adish, you too, take good care, all the best. Marissa, yes, certainly Marissa says congrats, indeed. Well done by the participants. Yasmin, so we will take the question as the Q&A, if that's all right. Roger, yes, you're correct. It's basically a tuning capacitor. Okay. All right, Desi. Yeah, I do like to pick on students in the class, so there you go. All right, yeah. Gary, also, you have a good night. Take good care. Be safe. Roger, good night. All the best. Kevin, you too. Have a good night. Thanks for the stuff you dropped off, man. Really appreciate it there. Okay, Jermaine, you too. Be safe. Take good care. They come next week. Sylvester, yes, certainly. Good night. Take good care. And congrats, man. Well done. Ramzan, you're certainly welcome. All the best. And Charlene, okay, yes, all the best to all of the students. Charlene is saying, you know, congrats to everyone. You too have a good night as well, Charlene. Thanks so much. And Adrian, you're certainly welcome. All the best. Yes, June, there are in-person exam from time to time, but remember there's a remote exam possibility as well. You can take it remotely or online, as we say, at any time, on demand. You too, George, have a good night as well. Sleep tight. Nikhil, you too, have a good night. And certainly, yes, do appreciate your congrats to the students. You know, everyone will appreciate, you know, celebrating, you know, the achievement. Very well done. Okay, Ian, yes, congrats to the new hams. And we know everyone here, once you stick with it and, you know, persist, we know everyone will be successful. Natasha as well, thank you. Have a good night. Take good care. All right, Desi. Well, yeah, I know it goes with Kevin and Anna there. So, but you have it on demand. You have the recording, so you could catch up there. That's why we try to do that. So we know life happens, things happen, and yeah, Kevin and Anna happens, and yeah, they distract you and take you away. But it's all good. So take good care as well. Have a good night. All right. Okay, John. Good night as well. Take good care. Jessica, good night too. Sorry, inside there. All right. Okay. You too. Blessings as well. Yeah, just catch up for the 1 hour. YouTube, you could, as I've been indicating to everyone, because it's streamed to YouTube, if you have Netflix, you're gonna have the YouTube app on your television, smart TV. So you can catch it and just search for 9Z4RG. That's the best way. And the playlist will come up for the general class and the technician class. Easy does it. So folks, take good care. All the best. Have a good night.